Hi guys, it's Kate, and this is day 3 of Math S-323. The first day we were introduced to vectors. The second day we were introduced to the dot product, one of the major vector operations, and now that we've had some experience with vectors in 2 and 3 and n-dimensional space, we're going to talk about what are the types of things that act on vectors. What are the things that take a vector and transform it into another vector? What are the operations that we do with vectors? And in fact, the objects that we're talking about are matrices. So in this class, we're going to learn the basics of matrices, the types of mappings or functions that they represent, the mechanics of how they act on vectors, and many useful properties and procedures that are closely related to them. So the first thing is a really basic definition of matrices. An M by N matrix over a field F is a rectangular array of elements of that field with M rows and N columns. So when you see a matrix, let's take a look, M by N. Here we have one, and we're looking at, note that this is a rectangular array of elements of a field. In this case, I have chosen the field of real numbers, as you will be working mostly in the field of real numbers in this class. And when we say the dimensions of a matrix, M by N, M, the first dimension, is the number of rows, which is on the left-hand side. And then N is the number of columns, so we can see that across the top. It's really important to note that the height of a matrix is specified first instead of the width of the matrix, because we're so used to thinking that left-right motion is the first component from working on the standard basis. That's just not how matrices work. So rows are specified first, columns are specified second. So in the set of n by n square matrices, addition and multiplication of matrices are always defined. In fact, they're really simple. If you have two square matrices that are exactly the same dimensions, the way that you add them together is that you add the components in the same place together. So if you have something in the first row, first column of one matrix and the first row, first column of another matrix, you just add those two together and they're in the first row, first column of the sum matrix. Multiplication is a little bit more complicated, but we'll get to it in a moment. But it is distributive with respect to addition, and we'll talk about that. And it's really important to note that matrices can only be added together if they have the exact same number of rows and columns as each other. So two matrices or three matrices, they can only be summed if they have the same number of rows and columns. Matrix multiplication is not commutative. You swap the order, it can change the product. In fact, a lot of the time if you swap the order, you may not even be able to compute the product. And so the n by n matrices do not form a field if n is greater than 1. So 1 by 1 matrix just has one single component in it. But once you get into square matrices with more than one entry, they do not form a field. They're actually said to form a ring, but that's outside of the purview of this class. So let's take a look at what types of transformations matrices represent. Matrices represent functions or mappings where we take one input and we give an output. We call that a mapping. Functions are mappings known as linear transformations. And be very clear with yourself that a linear equation, as in y equals mx plus b, is not the same thing as a linear transformation. So what is a linear transformation? A function f is called linear if the function value that we find when we have the function act on this combination of scalar multiples of vectors is the same as if we had it act on v by itself and then multiply the result of that function mapping by the scalar a, and then added on the function value if we had f act on w by itself and multiply that by the scalar b. So there are two things going on here. First is that the function value of the sum is equal to the sum of the function values. The other thing that's happening is that if you take the function value of a scalar multiple of an input, that's the same as taking a scalar multiple of the function value of a non-scaled input, written like that. So the way that we express that both of these things are happening is right here. Now what's interesting is that when you're working with vectors, we already explored in day 2's class on the dot product that any vector, and really even day 1, that any vector can be written as a sum of scalar multiples of standard basis vectors. And so this is a really useful fact to put to work with linear transformations. That means that if we had f, some function that was a linear transformation acting on the vector x, we could rewrite x as scalar multiples of the standard basis vectors, and then by applying what we call linearity, we know that that's going to be equal to f acting on each individual standard basis vector and then being multiplied by their appropriate scalar multiple. So this equality holds because of both this fact of linear transformations as well as this fact. This is extremely useful. This says that if we know the effect that a linear transformation has on every basis vector, we can combine multiples of those results together to determine exactly how the transformation affects any vector, because we can construct any vector using the standard basis vectors. We'll be putting that to use in some of our sample problems. Let's move right along. Now, we're going to state the exact same thing, so none of the material here is very new, but I wanted to introduce how we use summation notation when we're talking about matrices. So let's take a look at this statement. It says, stating this more formally, in order for some matrix A to represent the linear function f, which goes from fn to fm, remember that's the set of elements that are denoted by n tuples, I should say, of members of the field F, and we're mapping to Fm, which is m-dimensional. The ith column of the matrix A, which we will call, this is our notation for A sub I, must be the vector that we get when our linear transformation acts on the ith standard basis vector. What this means is that for any arbitrary vector v that can be represented as a sum of scalar multiples of standard basis vectors, linearity tells us that the function acting on the vector v is actually equal to each of the scalar multiples of the function acting on the appropriate standard basis vector. And when the function acts on the ith standard basis vector, it extracts the ith column of the matrix A. Now, this might be totally confusing, especially if you've never done matrix multiplication, but we're going to review that right now. There's a note right here in the margin, but I'm just going to sort of talk about matrix multiplication more generally, and if you really want to get into the nitty-gritty of this margin note, you're absolutely welcome to. When we talk about a function that's represented by a matrix, that is a linear transformation, acting on a vector, how does that happen? Well, say we have this matrix that represents some linear transformation, and we want it to act on the vector v, which is the vector 3, 2. The way we do that is we take this matrix, which represents the transformation, and we multiply it by v, and we put v on the right-hand side. Remember that v was 3, 2. Now, it's a little difficult to figure out exactly how to multiply lining up the linear transformation and the vector it's acting on in this way. The way that Paul and I really prefer when we're teaching, which really changes the game for a lot of people, even if they've learned how to multiply in another way, this makes your work much more organized. What we do is we line 3, 2 up, so it's sort of hanging right above the matrix. Here's what it looks like. And the way matrix multiplication works is first to note what the dimensions of the result of this multiplication will be. The product of this matrix and this vector is going to have the same number of rows as the matrix and the same number of columns as the vector. So it's going to have this dimensional shape. It's going to have 2 rows and 1 column. And it fits just like that. It sort of completes the puzzle right there. And the way we compute the effect of this matrix on acting on this vector is we take the sum of products of the following terms. I envision this vector as falling over sideways down into this matrix, sort of like a wood chipper. 3 times 2 plus 2 times 3, and the sum of those products is right there. So that's going to be 12 for us. And then, to figure out what the component is right here, again, falling into the wood chipper, but interacting with this row instead, we have 3 times 1 plus 2 times 0. So this is going to be 3 right here. Now let's take a look for a moment what happens when a matrix acts on a standard basis vector. So let's take a look at the first standard basis vector in R2. Now, following the same rules as we did before, note that the vector sort of tips over into the wood chipper. It's 1 times 2 plus 0 times 3, so we have a 2 right in here. And then we have a 1 times 1 plus 0 times 0, so we have a 1 right down here. Take a look at that. Because there is only a 1 in the first component, and the first component continuously multiplies this column, and there's 0 everywhere else, the only thing we end up with over here is whatever's in the first column. So when we have the matrix act on the first standard basis vector, it's going to extract the first column of the matrix. What if that had been the second standard basis vector? What if this had been 1, 0? Or, pardon me, 0, 1? Well, then we still would have had sort of ignored this part of the computation here and pretend that this is falling over into here. We have 0 times 2 plus 1 times 3. We have 3 here. 0 times 1 plus 1 times 0. We have 0 here. And sure enough, because the only factor that is non-zero continuously multiplies the second row, that's all that we're left with. Everything else gets multiplied by 0 when we are taking the sum of these products. And so that's how matrix multiplication works when matrices act on vectors. Also, when matrices act on each other, it's the same sort of lineup. You're taking, say this was a matrix right here, 1, 0, 0, 1. If we were multiplying 2, 3, 1, 0 by this matrix 1, 0, 0, 1, note that, first of all, this is possible. You probably have already suspected that not every single pair of matrices can be multiplied together. I mentioned that earlier. What's really important is that the number of rows up here matches the number of columns down here, right? So that when we wood chipper in, everybody has a buddy that gets multiplied to it. And then we can put that component right there, those products. So you need the number of rows here to match the number of columns here. And of course, if we follow the same thing, we'd have 1, 0, 1 times 2 plus 0 times 3. So we have 2 here. We have 1 times 1 plus 0 times 0. We have 1 here. We have 0 times 2 plus 1 times 3. So we have 3 here. And then we have, last but not least, 0 times 1 plus 1 times 0, which is 0 here. And so that's how you multiply matrices together. You sort of treat it like you're looking at separate vectors and seeing what the result would be. It's very interesting that I've somehow found some sort of matrix where when you multiply it by that matrix, it just returns the original matrix that we had to begin with back to it. That seems like it would be some sort of multiplicative identity. I can't tell if you can hear my pinky finger at my mouth, but I'm trying to give you some foreshadowing here. So this is what this is saying. This is saying that if I have this matrix that's trying to act on an arbitrary vector, we can break down that vector into a bunch of different multiples of the standard basis vectors. And when a function that's represented by a matrix acts on a standard basis vector, it extracts the ith column. So that's how we're able to simplify f acting on e sub I just down to a sub I, where I is, the a sub I means the ith column of the matrix A. So that's what that means based on how matrix multiplication works, the linearity of the transformations that we're talking about when we're using matrices, and the fact that we can write any vector as a sum of multiples of standard basis vectors. So let's take a look here for sample problem 1. So we're told the matrix of a linear transformation. Here's what we know about the function that it represents. Its domain and codomain are both R2. You guys know what domain is. Codomain is similar to image, but not quite. So let's think about a nice simple example of what a codomain is. Say we're talking about the function. We're going to depart from this problem for a minute. We're going to talk about a nonlinear function. X squared. F of x equals x squared. Now, what kind of elements do you plug into this? You plug in real numbers, right? Is there a limit on the domain? No, it could be any real number, right? So we say that the domain is a member of the real numbers. And then our output is x squared. So our codomain, the space where our output lives, is what the codomain is. That's a good way of putting it. Space where our output lives. The codomain is also a real number, right? When you square a real number, you're going to get a real number back. But when we think about an image, the image is the range of actual values that we get. So whereas all real numbers, that's the space, R is the space where the image lives, but the image itself is actually, well, x squared is only 0 and up, right? It's 0 and all positive numbers. So the image itself is that interval. So this is the codomain, and this is the image down here. Those are two different things. All right, so getting back to our sample problem, we have this mystery linear transformation, and so a matrix represents it. It's very important to note that the matrix is just the representation of this linear transformation. And we know a couple things about it. We know its domain and codomain are both R2. So that means that it takes vectors from R2 and spits out vectors in R2, which means that it's going to be a 2 by 2 matrix. And it's linear. It's a linear transformation. If a matrix represents a transformation, it's going to be a linear transformation. And so we know how it behaves. If you flip back to the previous page, we know the ways that we can manipulate it. And we also get two other clues. We get that when the function acts on the vector 1, 2, we get 7, 5. And when the function acts on the vector 1, 4, we get 11, 9. And so now our task is to find the matrix T that represents F, this linear transformation, by using linearity to determine how it behaves when acting with the standard basis vectors. All right, well, I don't see any standard basis vectors here. What we need to do is we need to sort of name these guys. We're going to name this first one V, and this guy is W. I should have made him a different color. There we go. We need to figure out how to create the first standard basis vector just using V and W. That's our first task, okay? Take a moment, try to do some scalar multiples, add, subtract, whatever you need to create the first standard basis vector, 1, 0. All right, how exactly do I do that? Well, I take a look at the fact that I need to zero out the second component. And the second component on one of them is 2, and the second component on another one is 4. So if I started with vector W, right, and I subtracted off 2 times vector V, I would at least have 0 in the second component. That should be a subtraction sign. All right, so I know that if I took W, which has 4 in the second component, and I subtracted off 2 times V, it would have 0 in the second component. What do I have in the first component when I do that? Well, I have 1 from W, and then subtracting off 2 times V, I have minus 2. So I have negative 1. So this guy right here is equal to negative 1 comma 0. And so the way for me to turn this into positive 1 comma 0 is to multiply the whole thing by negative 1. Now you may be wondering why I care so much about the first standard basis vector. Remember that when a matrix acts on the first standard basis vector, when a linear transformation acts on a first standard basis vector, it extracts the first column of the matrix that represents this transformation. So if I can figure out what happens when this transformation acts on E1, then I know what the first column of that matrix looks like. Let's take a look. I start out with the function f acting on 2v minus w, and by linearity, I'm going to be able to rewrite this. And this is great, because I know what f acting on v gives me and what f acting on w gives me. Now I have 2 times 7, 5 minus 11, 9, which, if we actually do the arithmetic, is 3, 1. And again, this is f acting on 2v minus w, which happens to be f acting on the first standard basis vector, which happens to be the first column of our mystery matrix, 3, 1. That's going to be the first column of our mystery matrix T. All right, let's see if we can construct the second standard basis vector. I want to find a combination of v and w that gives me 0, 1. Well, they both have 1 in their first component, so all I have to do is really subtract 1 from the other. So let's start with w minus v. If we take a look, w minus v is sure enough going to zero out those 1s up top, and then the second component is going to be 4 minus 2. So I'm left with 2 in the bottom. So I need to divide this by 2 in order to get 0, 1. So that's how I can create my second standard basis vector using v and w. Now let's have f act on this. Here we go. We use linearity to rewrite this as follows. And then we plug in what we know f acting on w and f acting on v to be. Our final answer is 1/2 of 11, 9 minus 1/2 of 7, 5. And we get 2, 2. Remember that that's the effect of f acting on 1/2 w minus 1/2 v, and 1/2 w minus 1/2 v happens to be E2. And f acting on E2 is going to give us the second column of our matrix T. So putting the first column of our matrix T together with our second column of our matrix T, we get our final answer is that T is equal to this matrix here that has 3, 1 as its first column and 2, 2 as its second column. That's T. And you can double check that by having T act on 1, 2, and it should give you 7, 5, and T will then act on 1, 4, and it will give you 11, 9. You will have a problem like this on your homework, in your small group work, so I wouldn't be surprised if this showed up on your exam. Alright, so some proofs about matrix multiplication and properties of matrix multiplication and other matrix operations are pretty straightforward. They're just kind of things you gotta do, so that's why we call it proving by brute force. So there are 2 things that you need to understand before we get started with any of these proofs. If you don't have these under your belt, these proofs aren't going to make a ton of sense, so it's important to get them very clear in your mind before we begin. One is that the way we prove that 2 matrices are equal is to show that an arbitrary entry in one matrix is equal to the same entry in the same position in the other matrix. That's the first thing. The second thing is that you need to be really well versed in using sigma notation and the matrix notation that we used earlier to call out components in various positions. So we're going to do a ton of examples of this, but let's take a look at the proof of associativity of matrix multiplication. So we need 3 matrices. We need A, B, and C. And what we really want to end up showing is that if we take the product of A and B and multiply that by C, that's going to be the same as taking A and multiplying it by the product of B and C. So the first thing we note is that A, B, and C are appropriate dimensions so that they can be multiplied together in the first place. And the matrix T is the product ABC. So when we take a look at this notation here, A is an n by m matrix. Remember, it looks like this. It acts on vectors in Fm, which makes sense because the vectors will fall into these m columns. And then it spits out a vector in Fn, which makes sense because the vector will be right here, so it has n rows. Then there's B, which is an m by p matrix, and that's going to map from Fp to Fm. Their product, A and B together, is going to be an n by p matrix. And then C is a p by q matrix, which can be multiplied with AB. And so ABC is an n by Q matrix. That means that the matrix T, which is the product of A, B, and C, maps from FQ to Fn as noted here. And note that this notation is really important. If I, j, that's the entry in the ith row and the jth column of A, then we can express the product of AB, I, k. So that means the entry in the ith row and kth column of AB, let's just pick an arbitrary place for that to be. So that location is the entry in the ith row and kth column of AB. And what does this mean exactly? That the entry in the ith row and kth column is sigma notation and it's Aij, Bjk. This is so crazy. Well, let's reflect on how matrix multiplication works. It means that we're going to take the entries along the same row as this particular position and the same column in B as this particular position, and we're going to multiply them together. And we're going to move throughout the columns in A, and we're going to move throughout the rows in B while staying in the same row in A and the same column in B to get that particular entry, the ith row kth column entry in AB. Now, what does that mean when we're summing that, or summing all those different products together? Well, that means that I want, if this is the ith row and kth column in AB, note that it shares the same row in A. So in A, we always are going to be in the ith row. But the column will change. The column will go from 1 to m. So that's why we have A, I, j, and j is the index of summation. That's going from 1 to m. And when we're multiplying these by their sort of partners, position partners in B, note that B is going to have the same column as this position in AB. So this is the ith row, kth column in AB. That means we're looking at the kth column of B, and we're going to start in the first row and then go second row, third row, fourth row, all the way down to the mth row, because there are m rows in B. And so that's why you see here that J, the row, is the index of summation. It's changing. But K, the column, is not, because that's how we compute matrix multiplication. So we're looking at this particular summation, and it is telling us that if we want the ith row, kth column of the product, that means whatever's on the left-hand side, we need to stay in that row. It needs to be the ith row of the A matrix, and the column will change as we move across. And we need to stay in the kth column of the B matrix, and the row will change as we move down. And that's how we take the sum of the products of those components appropriately. Now let's take a look at what happens when we look at A, B, C, I, R. Note that that's the ith column and rth row of the ABC product. Now I've pointed out here that's the ith row, rth column of ABC. So of course, just like before, this is the product of this entire row in AB and the corresponding column in C. And so when you go about writing this in sigma notation, you want to maintain the same row as this particular entry, so the ith row in AB, but the column is changing. So we're going to use K here. We need to include a different index of summation. We used J before. And then we have the same column as this entry, but the row is changing, and it is also going from all the way up from 1 to P, because we know this has P different columns, this has P different rows. And so we can write that like this, just like we did before, but doing A, B, and then C. And note that we're going to substitute in what ABIK is here. And so we're substituting in above. We now have two summation notations, and we're going to stop right there. All we've done is figure out how to show AB's ith row and kth entry, kth column entry, like this. Then the ith row, rth column entry of ABC, written it like this, substituted this in, and we're here. Now if we do the composition in the opposite order, this is where things get really interesting. We want to start with BC's product. Now if we look at BC, I'm not going to draw it out, but you're certainly welcome to. That means that the row is going to stay the same in B, the column is going to change. The column will stay the same in C, the row is going to change. So here we have, again, the index of summation stays, it's in the column for B and the row for C. And so that's how we express the jth row rth column of BC. Then when we do A, B, C, that order of matrix multiplication, we're looking at the ith row rth column entry. So that means that whatever is on the left-hand side, that row is going to be the same. So we have the ith row of matrix A, but the column will change. So that's why J there is the index of summation, and it goes from 1 to M. And then BC, note that the row will change, but the column will stay the same. So we have R out here. J is going from 1 to M. And then when we plug in what the jth row rth column entry of BC is, we plug in this sigma notation right here. Lo and behold, we have two identical sigma notation expressions. And these entries in this matrix are just members of a field. And so this term is the same as this term because multiplication is associative in the underlying field that that matrix is written in. Let's take a look at a simpler problem. This is a sample problem. We want to prove that matrix addition is commutative. So we're going to do the exact same process, but we're showing that matrix addition is commutative. We're going to show that the ith row jth column of A plus B is the same as the ith row jth column of B plus A. Here we go. Well, the ith row jth column of A plus B, we already realized that in order for us to add two matrices together, they need to be the exact same dimensions. And the ith row jth column entry of A plus B is the sum of the ith row jth column entry of A plus the ith row jth column entry of B. Now these entries themselves are just members of a field where addition is commutative. So we can rewrite this as the ith row jth column entry of B plus the ith row jth column entry of A. And by definition of matrix addition, how we carry out matrix addition, this is going to be the ith row jth column entry of the matrix B plus the matrix A. And so we've shown that the matrix A plus B is equal to the matrix B plus A. The only step here that needs justification is right here, and so that's the commutativity of addition. And we're done. That was field axiom 1 right here. Now we're going to learn a little bit about the determinant of an n by n matrix. It's a little bit like envisioning a black box, and into this black box you're going to slide the n columns of the matrix that you care about. In this case we're going to call it A. And the output of the black box is an element of the underlying field. Right now we're working in R. It has some defining properties. It's multilinear, so if you fill up any n-1 slots, so all but one of the slots, the output is going to be a linear function. Remember what that means again. A linear function of the vector that goes into the final empty slot. And it's antisymmetric, which means that if you swap two of the columns in the matrix, it's going to change the determinant by a factor of -1. And normalization, if you fill the slots with the standard basis vectors in order, the output is 1. So the problem with this sort of definition is that you usually have to prove that this function exists and that it's unique. They're normally just terrible types of proofs that really keep track of indices, but we'll be exploring its geometric significance in class. It's related to the parallelogram that's spanned by the columns of the matrix, but for our purposes, you can just believe me that the determinant is unique and that it exists. Let's take a look at how to compute a 2 by 2 determinant. So if you have a matrix where the entries are A, B, C, D, the determinant of a 2 by 2 matrix is AD minus BC. We're going to get into higher dimensional matrices determinants later in the course. Some other related matrices that it's important for you to know about are matrix transposes. The transpose of a given matrix A is written as AT with T as a superscript, and the two are very closely related. The rows of A are the columns of A transpose, and the columns of A are the rows of A transpose. So the transpose can also be found by reflecting the matrix A over the main diagonal of the matrix, which is the diagonal that's starting in the top left corner. So a few of the proofs we'll be working through will involve properties of the transpose of the matrix. So in the 2 by 2 case here, where we have A, B, C, D, the transpose is going to go A, C, B, D. You can think about that as reflecting over this diagonal. Or you can say, hey, this is in the first row, second column, so now it's in the second row, first column. Either way works. The other type of matrix that you need to know about is a matrix inverse. So a non-square matrix that's M by N matrix A can have a one-sided inverse. If M is greater than N, then A is going to take a vector in Rn, and it will produce a longer vector in Rm. And in general, there will be many, many matrices that can recover the original vector in Rn. And remember that this is a multiplicative inverse we're talking about, so when you multiply a matrix by its inverse, you should get the identity matrix back, which has ones along the diagonal and zeros everywhere else. And in fact, when you see something like IN, that means we're looking at the N by N identity matrix. That's a terrible drawing of it, but you get the idea. So if M is less than N, then A is going to take a vector in Rn. It produces a shorter vector in Rm. And in general, there is no left inverse matrix B that can recover the original vector in Rn, but there may be many different right inverses, and so A times B, this right inverse, will give you the M by M identity matrix. For a square matrix, it is possible for both a right inverse B and a left inverse C to exist. In this case, you can prove that B and C are equal. That's actually going to happen on your homework, I believe, and that they are unique. We can say that an inverse A inverse exists. For now, we'll be finding the inverses of 2 by 2 matrices using the following formula. The inverse of the matrix A is 1 over, here's the determinant of A, times this sort of manipulated matrix where the entries along the main diagonal are swapped and the entries off the main diagonal just change sign. So remember that A times A inverse will give you the identity matrix. Let's take a look at how matrix inverses can be so useful. This is the same problem as before. We have this matrix of a linear transformation. Here's what we know about the function. Its domain and codomain are R2, so we're dealing with a 2 by 2 matrix. It's a linear transformation. When it acts on 1, 2, it gives me 7, 5. When it acts on 1, 4, it gives me 11, 9. Let's take a look at how to write down a matrix equation and solve it for t. And that's the way that we're going to find t this time. Well, let's start out with our mystery, t. There's our mystery man, and we're actually going to take a look at the fact that when we multiply t by this matrix, we should get the following result. Does everyone agree with that? Remember that when t acts on 1, 2, we should get 7, 5 right here. This is just like matrix multiplication, ignoring the other column. And when t acts on 1, 4, we should get 11, 9 down here. Again, just like matrix multiplication, ignoring the other column. So let's write that out more clearly. The way that we solve for t is by finding the inverse of this matrix, by multiplying it on the right, which will make this the identity matrix, or the equivalent of multiplying by 1 when you're dealing with matrices, doing the same thing on this side, and then solving for t. Let's take a look at what the inverse of 1, 2, 1, 4 is. First, we take 1 and divide it by the determinant. The determinant of this particular matrix is 4 minus 2, which is 2. So we have 1/2 out here. Then we need to manipulate t. We need to swap the entries on this diagonal and change the sign of the entries on this diagonal. I'm even going to rewrite it a little bit neater. All I've done is distribute the factor of 1/2 to every entry. Okay, this, if we call this matrix A, this matrix is A inverse. We're going to multiply both sides of this equation by A inverse on the right. When we multiply A by A inverse on the right, we're just going to get the identity matrix. T times the identity matrix is going to be T. So we're left with T on the left-hand side. You can do out those steps computationally if you don't believe me. We need to do the same thing on the right-hand side. We need to multiply by A inverse on the right. Let's take a look at what that looks like. Lo and behold, the product of 7, 11, 5, 9 multiplied by A inverse gives us 3, 1, 2, 2, just like we got before, and that's our t. It was a way shorter process than the other way, where we had to figure out how to make standard basis vectors out of v and w. You should know how and why both of these work. And you should be able to do them both. It's a very valuable skill. Our last sample problem, well, I guess second to last sample problem, is this problem saying let A be the following matrix. We're going to assume that all 4 entries are positive and that A1 is greater than A2 and B2 is greater than B1. Show that the determinant of A is greater than 0. That's our first step. Well, that right there is the determinant of A, and it's greater than 0 because this term, A1 times B2, is going to be greater than this term because we're told that A1 is greater than A2 and that B2 is greater than B1. So in total, this term is bigger than this term. So we know that this is greater than 0. Now we have to show that we have to rotate the first column counterclockwise to align it with the second column. Well, let's take a look at the first column. It moves more to the right than the second column, but it doesn't go up as much as the second column. What does that look like? I've made my first column red and my second column black, so a simple drawing like this will suffice. The fact that A1, the component in the x direction or in the first standard basis vector direction, is greater than A2 means that that red vector needs to stretch more to the right, and it's not going to increase its second component or y direction as much as the second vector will, because B1 is less than B2. So that's enough to show that all you need to do is move in a counterclockwise direction to rotate the first column into the second. We're going to talk more about isometries and things like that in our next class, but that's sort of a sneak peek ahead. Our last matrix multiplication application is a Markov process, which is an iterated or repeated occurrence, something that happens again and again and again. And it can be represented by matrix multiplication many times over. Computers are usually used to speed these calculations up because it really stinks to have to take a 4x4 matrix to an extremely high power. But we're going to use a computer. Once we calculate the matrix detailing the probabilities of each event outcome, then each column will correspond to the prior state before the process in question, and each row will correspond to the future state after the process in question. And then raising this to higher and higher powers will tell you exactly, if I started with this type of state, what is the likelihood that I'll end up in this type of state? So you check out the column and the row. It's kind of difficult to explain in abstract, so I've included this example. You're playing in an unfair casino, and for any play, you may have 0, 1, 2, or 3 chips. When you bet a chip, you have only a 40% chance of winning. So that means there are some event outcomes that need some clarification. If you have 0 chips, you cannot bet, and you're going to continue to have 0 chips. If you have 1 chip, you have a probability of 0.4 of moving up to 2 chips, and a probability of 0.6 of moving down to 0 chips. If you have 2 chips, you have a probability of 0.4 moving up to 3 chips, 0.6 moving down to 1 chip, and if you have 3 chips, you declare victory and you walk away a winner. This never happens in Vegas. So let's create a 4x4 matrix that represents the effect of one play. Assume that before the first play you are certain to have 2 chips. Use matrix multiplication to determine the probability of your having 0, 1, 2, or 3 chips after 1, 2, 4, and 8 plays. Make a conjecture about the situation after a very large number of plays. Well, let's take a look. We want to construct an array of probabilities. This is going to be a 4x4 matrix because the 4 possible states are having 0, 1, 2, or 3 chips. So we draw the outline for our matrix. The columns correspond to your state before the round of play. So I'm going to say that this column is 0 chips, this column is 1 chip, this column is 2 chips, this column is 3 chips. And then the rows correspond to your state after the round of play. 0 chips, 1 chips, 2 chips, 3 chips. Now let's fill this in. If I start with 0 chips, I'm looking at this column. The instructions tell me that if I have 0 chips, I can't bet, and I'm going to continue to have 0 chips. So if I have 0 chips, the chances of me having 0 chips after the round of play is 100%. So there's a 1 right here. There's no chance that I will have 1 chip, there's no chance that I will have 2 chips, and there's no chance that I will have 3 chips because I cannot play if I have 0 chips. Now, if I have 1 chip before the round of play, There's a 40% chance that I'll have 2 chips after the round of play, and a 60% chance that I'll have 0 chips after the round of play. So we're going to put 0.6 here, where we're looking at the location for 0 chips, where there's no way to just stay, and there's 0.4 there and 0 there. Now if we start with 2 chips, there's a 0.4 chance that we'll get 3 chips after our round of play, and a 0.6 chance that we'll have 1 chip after our round of play. So we have 0. There's no way to get 0 chips after 1 round of play if we start with 2 chips. We have 0.6 here. There's no way to have a neutral bet either. And 0.4 down there. And if we have 3 chips, we declare victory, we don't bet, we continue to have 3 chips, we walk. So 3 chips means that there's a probability 1 that we'll have 3 chips after our round of play. So this is our matrix A. Let's take a look. Our probability of having 0, 1, 2, or 3 chips after 1, 2, 4, and 8 plays. Okay, well after 1 play, we started with 2 chips, so we want to look at this column. And in fact, we'll always be looking at this 2-chip column because it's saying, hey, this is what you started with. 2-chip column. Well, we have a 0.6% chance that we'll have 1 chip and a 0.4% chance that we'll have 3 chips. How about after 2 rounds of play? Well, all we have to do is square this matrix and then look in the same column. I've used Wolfram Alpha to square this matrix because I am just too delicate to have to do it out by hand. And here's what the column that is the 3rd column, which corresponds to 2 chips, looks like. So this is A squared, and we're still looking at this particular column that's going to tell us the probability of each occurrence. If we started with 2 chips, and then after 2 rounds of play, what this is telling us is that we have a 0.36 probability that we'll have no chips. That's pretty high. We have a 0.24 probability that we will have 2 chips. Basically, we gained 1 and then we lost it. And then a 0.4 probability that we'll have 3 chips. If you wanted to know how many chips, what's the likelihood that you'll have however many chips after 4 rounds of play, you want to take this matrix and raise it to the 4th power. Maybe you're interested after many, many rounds of play, raising it to the 8th power, to the 16th power. In this problem, I actually specifically wrote 1, 2, 4, and 8. And you're always going to watch this column that corresponds to, I started with 2 chips, what's the probability I end with 0? 1, 2, or 3 chips after however many rounds of play I'm interested in. As luck would have it, as you keep getting higher and higher and higher powers of this matrix, it seems like the 3rd column of this matrix is practically approaching a limit. And in fact, as you take this matrix to higher and higher powers, the 3rd column gets very, very close to having 0.472 in the first component, then 0, and then something that's really, really approaching 0 quite nicely. This is actually the 3rd column when you raise this matrix to the 8th power. And then down here we have 0.52957. And it seems that when you raise it to the 16th power, that first component really starts to approach 47%. The 3rd component starts to approach 0, and then the last component starts to approach 53%. So it seems like you have a 47% chance that you will end up with 0 chips if you just keep on playing, and a 53% that you'll end up with 3 chips if you keep on playing. That's quite something. The odds are really against you, because remember, you started with 2 chips to begin with. This is just a really nice example of how matrices can be used in probability theory. You won't be doing any problems like this in your group work, but you will be working with proofs of matrix computations like multiplication and addition, and then some interesting ideas with linear transformations.